we consider it with you integrable functions, and in integration, indeed, we integrate not over the whole set, but only over so-called support. And I use these terms. I use this term a few times. So what is the definition? Given measure mu, a measure, we will say that support of mu is defined as x such that in the whole space, such that for any neighborhood, it's supposed that mu is Borel measure. Mu is Borel measure, so it is well defined on open sets particularly. For any neighborhood of x, neighborhood u of x, we have that measure of u is positive. Measure of u is positive. We can't say that measure of x is positive. For example, for Lebesgue measure of any point is 0. So it's important that for any open set containing x, measure of this set is positive. It is the same equivalent description, or it is not difficult to show that if you use the definition that the corresponding set is closed. Why? Since if you have sequence of points from support and we have some limit point, then, and if you take any neighborhood of this limit point, then in this neighborhood there will be some neighborhoods of points from the sequence, and the measure of them will be positive. So definitely this point also belongs to the support. So set is closed. Another description, some people include this definition, the property closeness, some not. So indeed, this is the largest. It is the largest closed set F, such that for any open set G with non-empty intersection, G intersection to F is not empty, it follows that measure of this intersection is positive. So this is the definition. It's not the same. Maybe about properties firstly. Properties of support of measure mu, easy to see. The first one, if we have A is measurable set, and such that A is disjoint to the support of measure, then of course we have that measure of A is 0. Follows from definition immediately since it's outside of the support. And the second one, that indeed any integral of any function over the mu for the whole space, it is integral only over the support, by this simple remark, support the mu. So always we integrate any function only over the support of measure. Only over the support of measure. Support, in some situations, it's useful to consider another concept which is closed to support. It's so-called carrier of measure. Carrier of measure mu is defined in the following way. Of course, again, it's supposed that measure is Borel. It is a Borel set. It is Borel set C, which is Borel set such that we have that for any set A measurable, for any set A which is inside on the complement, in the complement we have that measure of E is 0. Measure of E is 0. So carrier of measure, it is the set. Of course, it would be great to have largest set with this property, but not always we can do this. The set, now it's not closed, only Borel set, such that if you take any set from the complement, that measure is 0. So indeed it is the set, both sets describe somehow the set where the measure mu lives. It exists on the set, outside it is 0. Why these two concepts are not the same? Look, it's a very simple example. If you take measure mu, which is defined only on rational, mu on the set of on the whole line, and let it will be defined on any subset of the line. and be such that this measure be such that it will count only rational points. For example, we have that measure of E. By definition, it is the sum of 2 minus n, and we take summation for all Qn inside of E. We consider it measured like this. This is very good finite measure. Here, of course, Qn, it is set of all rational. Okay? So, this is a measure, finite measure, Borel measure, of course, since this collection is, contains Borel sets, at least the restriction is Borel. Now, and what do we see now? We see that for any rational number Q, the measure of Q is positive, Therefore, clearly in any neighborhood we will have positive value. Therefore, we have that support here of measure mu, it is the whole line, of course. Yes, because for any point. Now, but here, carrier of measure mu, it is only the set of rational, since if you take complement, then complement is 0. Now, so this is related to problems that I started last time about integration of function, integration with respect to a measure which is given on some sequence. So let us repeat this argument. So if we have a measure of that form, that is, if you have that measure of set E, it is just the sum, and here some mu an, in principle, it's not now convergent series, maybe diverges. And if you take summation for all an inside of E, an is some given fixed sequence, for some given fixed sequence an, yeah? Then what do we have? Then we understand what is the integral with respect to this measure. Then for any function f now will be measurable with respect to this one. Then for any we have that integral of f d mu. It will be just the sum and nothing more. It will be the value of an and mu of an for all over the any set E. Again, summation is the same. Of course, not always function is integrable. Depends on convergence or divergence of the series. Now I want to give you an example which is interesting for people working in so-called potential theory. In potential theory, the people considered different potentials, and they are given a solution to some fundamental equation in the space. And in the plane, this solution, this function which defines the potential is a logarithm of 1 over z minus zeta, if you want to integrate. Then what is the, maybe let's take only this one, z. So this is the function. It's more, we consider this function in the complex plane. In the complex plane, of course, it has singularity at 0. Now look, for any measure mu, given measure mu, it's usual, it's supposed that measure mu is Borel, and compact support mu is compact, that is bounded set, compact. And what else is usual, the people consider it in this situation probability measure, normalized measure of the whole space, and it measure of its support is 1. We will define some function. We will define the function u mu of z, which is just integral of logarithm of 1 over z minus zeta. And we integrate with respect to this zeta. So z is a point here, fixed point. For this fixed point, this integral exists. And then, maybe, depends on measure. And then it will define so-called potential. This is logarithmic potential. Potential of measure mu. It's possible to show that this potential indeed has some good enough properties. Also, we can define so-called energy, logarithmic energy, corresponding to this measure. This logarithmic energy is defined as the integral of potential. And now we, again, integrate with respect to the same measure. But now z is variable. So now it is a number, or maybe infinity. Number or maybe infinity. So it's possible to show if measure has compact support, then this integral cannot take, for example, value minus infinity, but it can take value plus infinity. Now, and this is so-called logarithmic energy. Logarithmic energy, of course, corresponding to the measure mu. And eventually, we will take, suppose we have compact set K. We have a compact set K. A compact set K. And we will consider now, we will define now IK. No. Then there exists, it's possible to show that there exists measure, so-called equilibrium measure. Equilibrium measure, let's denote this measure in this way, such that we have that integral with respect to this logarithmic energy, with respect to this equilibrium measure, it is infimum. Infimum of all integrals, infimum of course energy, it is double integral of this potential logarithmic function, infimum of logarithmic energies with respect to measure mu, where we take infimum for all measure mu with support of measure mu inside of compact set K, of course again Borel, and we have that the measure of the set K is 1. Okay, so we consider infimum for all probability measures. The measure is 1 on the complex plane, but such that support is inside of this compact set K. So this value is very important in potential theory. This is minimal energy. There is a theorem that shows that for good situations this infimum exists, and no, infimum of course always exists. For good situations this infimum is finite, and if the infimum is finite, then the corresponding measure exists. Corresponding equilibrium measure exists and indeed unique. Okay? Now, why do we consider with you this example? I want to illustrate the simple fact that you can meet in many books in potential theory, that if compact set K finite or countable, then we have that set is polar. Polar, it just means that this minimal energy is infinity. So this is one of the definition, by the way. K is polar. It's called, it's not unique definition. There are many other ways to describe this. For example, we can define it if we have that this E mu E, this infimum of this I mu is infinity. So it means that that is for any measure mu with this property, we have that I mu is infinity. In particular, for example, if K is finite or countable, then we will have that K is polar. That's not inverse, since for small counter sets they are uncountable but also polar. Okay, but classical counter set not. Okay, now look. Let's show this. So this is exercise in integration, indeed. Exercise in integration. So what do we have? Consider for simplicity finite set. We have that K, it is just the ZK, Zn from 1 to n capital, some collection of points, nothing more. Finite set. And we have a measure. What does it mean? Then for any measure with this property, any mu, okay, maybe I have to denote this somehow, but it's clearly that measure satisfying this condition. We have that measure is 0 everywhere except these points. Yeah, we have some mu of Zn, and the sum Zn from 1 to n equals n capital. So it is just some collection, finite collection of non-negative values, nothing more. Then what is the potential? What is the potential? If you take potential u mu of z, then we understand with you what is the integral. Okay, I just erase it here. What is the integral with respect to this finite or countable measure? It is just summation and nothing more. It is logarithm of 1 of z minus, we take summation for this point zn. Zn, and of course here we have to multiply by mu of zn and take the sum n from 1 to n capital. Here, this is 1, and this is n capital. So please your questions. Is it clear? Yeah? So this definition of integral. Now what do we have? And we have that integral of I mu. Now we will integrate this function. We integrate this function with respect to z, of course. Now we integrate with respect to this function, but only on this finite number of points zn. Then what do we see? We see that this integral is infinity since, why it's infinity? Since at least one value mu of zn is not 0, since the sum of them is 1. The sum of them, at least one of them is positive. At least one of this value is positive. And then what do? We take this, we take the corresponding value mu zn and multiply by the value of the function at this point. But value of the function at this point is infinity. Of course, we understand with you that if function, for example, identically equal infinity, it's not a big problem for us if we integrate this function over the set mu and over the set e with 0 measure. Yeah? It's not a problem. We can integrate functions that have infinite value. But if it has infinite value on set with positive measure, then integral, of course, is infinity. Integral, of course, is infinity. Just the case. Since we will integrate now this with respect to measure mu, it means that we will have to take, what is this integral? So this integral, it is the sum n from 1 to n capital, maybe now m, and here we take sum n from 1 to n capital, and here we have logarithm 1 of zn minus zm, and here we take mu of zn, okay? So it is just means that we have to take at least one infinite value. Mu zm. Okay? If we will do this, so we will have this as infinity, since at least one value of mu at one point is infinity. So it means that finite compact set is polar, integral is infinity. Okay. Now, this is just illustration. Now, okay, now as I promised, let us consider we do not have enough time. But nevertheless, let's consider some problems about integration. It will be bonus for you as attending students. Okay? Now, what kind of problem we have to meet here? One problem about the support. This problem I gave last year in the midterm. So this is midterm 2, problem 3 in this year 2008. So again, not difficult if you understand what is support. We have mu is Borel measure on over C of a complex plane. And we have that, the problem is to show that support of measure mu is infinite, countable, uncountable, don't know, infinite, if and only if we have that integral of p squared d mu. We have this implication. Integral p squared d mu equals 0 implies that p equals 0 identically for any polynomial. So in this way, I know the set of all polynomial. Okay, so measure mu is infinite. Support of measure mu is infinite. It means it contains at least infinitely many points, countably many points, if and only if we have this implication. That is, for any polynomial, that square of polynomial implies that polynomial identically 0. Let's see that indeed it's true. for this implication, by contradiction, we have that, or maybe let's take firstly, wait a minute. Let's firstly prove this one, if you not object. So, we want to prove that measure is infinite. We want to prove that measure is infinite. By contradiction, measure mu is finite. It means, support is finite. It means that support of measure mu, it is just some collection z, n from 1 to n capital, nothing more, support. Then, clearly, what should we do? We will take just kind of interpolating polynomials which will have value at that point. Then we can take polynomial p of z, which is the product z minus zk, or zn, n from 1 to n capital. So this is some non-zero, of course. It's some non-zero polynomial. And clearly, we have that integral of p squared d mu. Of course, it's the zero. Yeah? By definition, again, of this integral. Because it is the sum of the value of the zk and the mu of zk, n, it's also important, k, and k from 1 to n. Of course, this is zero, space p squared. Yeah? So, we have this immediately. For the inverse implication, suppose now that support is infinite. Support is infinite, again, by contradiction. By contradiction, what does it mean contradiction? It means that there exists some polynomial such that the integral is zero, but polynomial is not identically zero. That is, by contradiction, there exists polynomial p such that integral p squared d mu is zero, and p is not identically zero. If p is not identically zero, it can be written in that form. That is, we have that polynomial, it is just the product of z minus zn. From 1 to n capital. Any non-zero polynomial we can write. Of course, maybe with repetition. It's also important. Now we have only finitely many points here and infinitely many points in the support. Yeah? We have that support of measure mu is infinite. Therefore, we can take, there is at least one point. There is the point y in the support of measure mu, such that this point is distant, such that we have the distance from y to all that zn, it's some positive number, more or equal than delta, for all n less or equal than n capital, since there are n points, and of course we can take y something outside of that one. Indeed, for the plane we can take here as large as we want. For example, we can take here 1 million, okay? Now, and then what do we have? Then we will have, if we take the ball with small enough radius. Okay, let's take immediately 2, for example. Why not? Since there are finitely many points on the plane, we can take the distance as large as we want. Then we will take the ball, for the ball B, closed, for example, ball. For closed ball B, closed ball K at point, with centrum at point Y with radius 1, we have that integral, or we have that P over this set. Of course, is positive, yeah? It's positive and P squared. It has some value bounded from below. It's smaller than some, larger than epsilon 0, trivially, yeah? Since the polynomial has 0 only here, of course, on this ball, it will be distant from 0. So, we have that integral of P squared d mu now is more or equal than some epsilon 0, and the measure of k, this is k, yes? Okay, in the definition, indeed, okay, we can write B. Since in the definition we have to consider open sets, it's not so important. Measure B1, and this is positive also. This is strictly positive. Why? Because Y from the support. Y from the support, so this is some concrete positive value. Why it is larger? Because we will put there measure of closed ball, but measure of closed ball, of course, is larger than measure of open ball. Measure of open ball is positive by distance point from the support. So the problem was not difficult, but as I remember, indeed, well, the students did not solve it. The second implication. Okay, so please your questions about this problem. Now Now, some problems about characterization when function is integrable. Very often, the characterization, the problem of the type, given function with some conditions, usually measurable, maybe some inner conditions there are, to prove that function is integrable if and only if, And some characterizations very often in terms of the set, in terms of this measure of the set En. I will denote by En, given function f. Let's consider the set. Indeed, we considered this before. E, when we prove Egorov theorem and some other theorems, such that we have that f of x more or equal than n. So this is good measurable set. Now, and these characterizations, these problems, as usual, they can be solved by means of rather useful Chebyshev inequality. So, what is this Chebyshev inequality? Chebyshev inequality. Chebyshev inequality is the following. Suppose that function f is integrable on the set E, then we have that measure of the set can be estimated. Then we have that measure of the set can be estimated from above by 1 over n and integral of modulus f, and here d mu, of course, integral over the whole set E. Of course, this is not difficult to see this inequality, yeah? So one can say that inequality is trivial, but it is rather useful, important in many situations. So this is, it has personal name, Chebyshev. Of course, we understand that indeed, what do we see? We see with you that integral of f d mu over set E more or equal than integral over the set En, since function is non-negative. And on this set, function is bounded. So, of course, it is more or equal than n and mu En. So we will have this inequality. Yeah. Now, what kind of problem we can prove now using this Chebyshev inequality? Let's consider this as a corollary. The first corollary is the following: function is integral of positive function, or maybe modulus. Integral of modulus of f d mu is 0 if and only if f is 0, almost everywhere. The first inverse implication is trivial. It's clear by definition of the integral. By definition of the integral is 0 function, of course, integral is 0. And second one, I mean direct one, immediately we have by the Chebyshev inequality, yeah? By Chebyshev inequality, because if we have that this integral is 0, it means that measure of En, the set En, we have that measure of En goes to 0 as, no, it's not quite good. So, by Chebyshev inequality, we have that this integral is 0, so we will have that mu of En is 0 for any n. So it just means, maybe it's better to write here t. Here, since indeed, maybe it's better to formulate this t immediately for any t. So t is not for any t which is positive. Of course, it works. This proof works for any parameter, not only natural. And now, if we have this for any t, it just means that function is 0 almost everywhere. But there is another proof of this implication, another proof, also useful as illustration of standard technique in the theory of measure and integral. This standard technique is the following. We want to show that function is almost everywhere 0. So let us consider the set A, which acts such that function is positive. Modulus of function is positive. Okay? So we want to show, what do we want to show? We want to show that measure of the set A is 0. If it's true, then we have that function is 0 almost everywhere. Now, we cannot integrate over this set. Of course, we can integrate, but we cannot say that integral over the set A modulus of f is positive. Why? Because this is only positive, there is no bound from below by some concrete value, but we can overcome this very easily. Can take this, represent this as a union, k from infinity, ak, and ak, of course, is defined as x such that modulus of f more or equal than 1 over k. It's clearly that we have this representation, yes? And now, if we suppose by contradiction, that this measure is positive, that measure of A is positive, then by sigma additivity, we have that there exists K such that measure of set AK is positive. So now it is very concrete value delta, which is positive. Then, of course, we will have a contradiction F d mu, which is 0 on one hand. It is more than integral over, more or equal integral over set AK of modulus F d mu. But this function now is bounded from below by 1 over k, and now we have this delta. So definitely it's impossible, okay? So this is usual method, useful method, but of course, Chebyshev theorem here, Chebyshev inequality here gives immediately result as a corollary. Now, and there are other problems that I want to give you a few of them. What else can we say from, what can we conclude from this Chebyshev inequality? From Chebyshev inequality, it means that function, if function is integrable on the set E, then by Chebyshev inequality, we have that this n and mu of En is bounded sequence, yeah? The sequence is bounded from 1 to infinity because it is bounded by the value of the integral. We have the sequence is bounded, but there is no inverse implication. There is no inverse implication. It's enough to take function 1 over x. 1 over x on the interval 0, 1. Function, of course, is not integrable, since it's not Riemann integrable. Here, this is bounded, yeah? We will have that n and here mu En, it is just 1 and difficult to see. Yeah? Is it clear? Yeah? Because we have function, and here, if we have n, then this is just 1 over n, and this function is 1 over x. Okay? Now, and what is more? What is more? Even in the case, we can ask something stronger. We can say, okay, not only bounded about inverse implication, but let it will be 0. Yeah? That we can write even more. If we have that n and mu En goes to 0, of course it's stronger than boundness, yeah? It does not imply that function f is integrable on the set E. Take for example now f of x equals 1 over x, and here modulus of natural logarithm x on the interval 0, not 1, let's put here something as 1 over 2. For this function, I recommend you to check it. It's not very difficult. If you take this function f, x, and here natural logarithm of x, then this function will be a little more close to y-axis, yeah? And then given n, we will decrease now this value. And now this value for this new function, but integral area will be till now, this area is infinity. This integral diverges, not difficult to see. But now it will be something as 1 over n and natural logarithm of n. So if you multiply by n, we will have 0, okay? So it's interesting question. Of course, if we will ask something more, if it will go to 0 more fastly somehow, then we will have this condition. It is just the problem from your homework. From your homework, the problem number what? 2. N1. And problem number one, if measure is E is finite, then we will have that f is integrable if and only, of course, suppose that function is measurable, if and only if we have that the corresponding, this is description in terms of this mu In, yeah? So now we want to have that mu n is finite, convergent series. It is something, again, stronger than that one, yeah? Because if this is 0, of course it doesn't mean that this is convergent series mu n because of that example, okay? So I'm sure that you will prove this. If not, then I will help you. So there is this nice characterization. Some other characterizations of the same type are problems. In these problems, the condition is given in terms of the, not sets En, but something pre-images for some strips. Pre-images for some strips. So if you look in different books, in theory of integral, you will find many problems of the following type. So what are typical problems? Typical problems are, by the way, this is only for finite measure. You will see that you will analyze the situation when measure is infinite. So typical problem, this is example number 2. It was example number 1, or maybe let's write this as a problem number 1, or maybe this remark. This remark, it is problem 1, now problem 2. So it is given for some natural as usual. So P here, 2, 3, 4, etc. You can write it, yeah? And then we will have the problem of the following type. Again, mu e is finite. By the way, it's rather close to the previous one. And we have function is measurable on the set E. Let be non-negative function, non-negative. Then we have the characterization that function is integrable if and only if. If and only if condition is given in terms of convergence of some series. So this is close to the previous one problem. For example, it can be done in terms of the following series from 0 to infinity. Here we have pk, and here we have mu x, such that pk less or equal than f of x less than pk plus 1. So there are problems of that type. If you substitute, no, it's not quite good. It's only more or equal. It's enough. Okay, let's take only that one. Okay, so there are problems of that type. Also, the case mu equal infinity shows that this is important restriction. And there are some other conditions of that type, or another the condition that function is integrable if and only if k, and here mu k less or equal x such that k less or equal than f of x less than k plus 1 converges. There is no condition, converges. The series converges, etc., etc. And the one problem I found in the book of Bogachev, in this book, there is explicit value for the value of the integral. So Bogachev suggests the following problem. We have that function is non-negative, function is integrable. Then, also I recommend you to check this. We have that integral of f d mu can be written as a kind of sum of that type, but now it is a limit. It is a limit, r goes to 1 decreasing way. Here summation from minus infinity to infinity with respect to k or n. And here we have Rn mu of x such that Rn less or equal than f of x less than Rn plus 1. Of course, all these problems are rather close one to another. Okay? So now not only, of course, existence of this limit, it will be the guarantee of integrability of the function if we have this condition. So, but now it is just exactly the value of the integral. Okay. Now all these problems can be solved just by considering pre-images of small strip. The problem is how to arrange all these strips. Okay. Since if you will consider the strips, we can estimate now the integral from below, from above, if you consider it as putting simple function. So this is good. Now, the next kind of problems is related to calculation of the limit. If calculation of the limit, So definitely, almost definitely, this is Lebesgue-dominated convergence theorem or Fatou lemma, maybe monotone convergence theorem. So now, or maybe this is a problem of the type that function is integrable. Function is integrable. So what is class of problem 3? Calculation of the limit, find the limit. Calculate some limit. It's usual of some integral. So once more, almost definitely, you have to apply some of these theorems. Fatou lemma, monotone convergence theorem, Lebesgue-dominated convergence theorem. Or function is integrable, for example. Function is integrable, and we have something f and some integral is 0, something depending on n for any n. It shows to prove that function is 0 almost everywhere, or something like this. I will give you a pair of examples if you do not have questions about this, the second example. At the beginning, one of the problems from homework just is the question of the type. Simple stuff. Simple stuff. We have e equals 0, 1. We have that integral, f is integrable on the set E. Then what we have? We have that integral f xn f dx, or Lebesgue measure, goes to 0. Of course, it's immediately Lebesgue-dominated convergence theorem. Somebody is asking, looking for you. Huh?
My mom checks
Maybe,
whether I
maybe something happened. You can.
no, she checks whether I wake up or not.
Yeah, you can say that you do. Of course, here it's trivial, yeah? Lebesgue-dominated convergence theorem. Almost the same. Okay, the same you will see in your homework, so I will not repeat that. Now, the problems of that type, or the problem of that form. Function is continuous on the interval 0, 1 condition, yeah? And we have that integral of f xn dx is 0. Now suppose this is Riemann integral, function is continuous, no problems. Then the question is to show that function is 0 identically. Of course, it's supposed that here this integral is 0 for any moment, so-called moments integrals. All moments of functions are 0. Then function is 0. Why do we have this implication? Your suggestion. Do you see or not immediately solution? There is nice Weierstrass theorem. Weierstrass theorem says that there exists sequence of polynomials Pn that converges to our functions, this function is continuous, uniformly, not only pointwisely, uniformly. And if we have, so you can say that this problem not from the theory of Lebesgue integral, since here we can solve just using the concept of Riemann integral. Since if we have uniform convergence, in general, what is the problem for Riemann integral? Pointwise convergence of sequence of functions is not a guarantee that convergence of integrals, but uniform, it's guarantee. Therefore, we will have that integral of Pnf dx will converge to integral of f squared dx from 0 to 1, yeah? By uniform convergence. But all of these integrals, of course, are 0, because Pn, it is the linear combination of monomial, finite linear exponents. Therefore, we have that this integral is 0, and from here it's easy to see that function is 0 identically, because integral of square is function. Now look, similar problem. Suppose that function is integrable on the interval 0, 1, for example. Yeah, let's take on the interval 0, 1. And suppose that now this is Lebesgue integral. Xn f dx, or dm as I wrote before, Lebesgue integral. All these Lebesgue integrals are 0 again for any n from n0, which is the set, etc., etc. So the problem is the same, to show that function is 0, but now, of course, almost everywhere, since we cannot control the set of 0 measure. Now, what to do? Of course, we can try to use the previous method, but then this is the problem, that if function is integrable on the interval 0, 1, of course it does not follow that f squared is integrable, yeah? Sure, you understand this, yeah? 1 over square root of x. 1 over square root of x is Lebesgue integrable on the interval 0, 1, but square is not. Therefore, if we will try, of course, we can choose the sequence of by Lusin theorem. By Lusin theorem, we can choose sequence of continuous functions, therefore sequence of polynomials that converges to f not uniformly now by pointwisely, but then we cannot use theorem of passage to the limit because of the lack of the integrability. But here, there is a nice idea that there exists by Lusin theorem. By Lusin theorem, there exists a sequence of polynomials Pn that converges pointwisely to sine signum of f. So you understand what is this function, plus minus 1, yeah? If function is positive, this 1, and minus 1. So if function is measurable, then if you have that function is measurable, then sine of f is measurable, not difficult to see. Maybe what is what seems to me, I give you something like this in the homework, you see. Now, therefore, what can we apply? It's not all. And we can take, it's not difficult to see if you look at the proof of the Lusin theorem, that if function is bounded, if you use the approximation by continuous function, we try to approximate by continuous function f, and if function is bounded by m, then we can also take bounded sequence, but in principle, it's enough to take Pn modulus lesser or equal than 2, since sine is lesser than 1. And then what we will have? We will have that we can apply Lebesgue-dominated convergence theorem, okay? Then we will have that Pn multiplied by f convergence pointwisely, yeah? Pointwisely to modulus of f, of course, if multiply v modulus f, yeah? Now we have that Pn f modulus, it is bounded by 2 modulus f, but is integrable on the interval 0, 1, yeah? Since function is integrable. We can apply Lebesgue-dominated convergence theorem, and then we will have that integral of Pnf, which is 0, by the same arguments, converges to integral of modulus of f d mu. But, so this integral is 0. We have that integral of modulus f is 0, but we understand that from here f is 0, almost everywhere. Okay, so please, Mehmet, your question about this problem. So we can do this also. Now, question? Now, the last type of problems, maybe let us consider with you next time. So, once more, keep in mind that if we have condition of that form, or maybe sometimes with sine nx, f, etc., then you have to understand what kind of polynomial we have to use. For example, here the polynomial, once more I will repeat, the polynomial that converges pointwisely to f, we cannot apply by the argument that function, we cannot apply Lebesgue-dominated convergence theorem in that situation, okay, since f squared in general is not integrable. Okay, tomorrow we will start with you new chapter about differentiation of indefinite Lebesgue integral. I forgot, since I have a half of minute, I want to say the one thing that I forgot to do at the beginning, that as usual, you can, more often we met, one can say that carrier of measure may be better since it is just the set such that outside of the set measure is 0, yeah? And so in support of measure, we include some points when measure has a 0, some points such that measure on the set is 0, since if you take the closure. But the support is more useful indeed, since the carrier of measure is not well uniquely defined, one can say. For example, if you take measure mu as Lebesgue measure on the line, yeah, then what is carrier of the measure? Then we can say the carrier of measure mu, it is the whole line, for example, by definition. Or we can take line minus any point. So what is the definition of carrier? Carrier, it is such that x minus this carrier, yeah, the measure is 0. The measure is 0. It has here this property. Or we can take r minus z for any z such that measure of z is 0, minus counter set, etc., etc. Okay? So very good measure, Of course, this may be the best form of the carrier, but also this and this and this, they also can be taken as carrier. Therefore, as usual, people, they consider it something related, some minimal value of some function or some integral given on the carrier, but not carrier as a set. They consider collection of all carriers. Okay, now that's completely all. I hope to see you tomorrow.